Hello, everybody, and welcome to the ELECOMP Capstone Virtual Summit of Spring 2021. I am Christopher Machelitis, joined here today with my colleagues Peter Palaio, Joshua Clift, and Colin Sullivan. We will be presenting our iXblue Precise Point Positioning Global Navigation Satellite System Receiver that we have been working on since September. This project would not have been made possible without the help of our technical directors. From iXblue, we have Gueric Morvant, a software engineer, Jean-Baptiste Lacrambe, a research and development navigation solution manager, and Elliot Tadoldi, an inertial navigation and GNSS research and development engineer. From URI, we have a 2019 graduate, Jeremy Peacock, who majored in computer engineering and computer science, along with a minor in Japanese. This project team is comprised of 2 electrical engineers and 2 computer engineers. Starting on the left, Joshua Clift, an electrical engineer with a minor in German. Myself, Christopher Machelitis, the team leader, with a major of computer engineering and a minor of computer science. Colin Sullivan, an electrical engineer, and Peter Palaio, a computer engineer.
iXblue is a global high-tech company specializing in design and manufacturing of advanced autonomous, marine, and photonics technologies. The group's in-house expertise includes innovative systems and solutions devoted to inertial navigation, subsea positioning, underwater imaging, as well as shipbuilding, test, and simulation means. Underpinned by its unique in-house technologies, iXblue offers turnkey solutions to its civil and defense customers to help them conduct their sea, land, and space operations with optimal efficiency and reliability. iXblue is one of the first companies in the world to exploit, develop, and bring to the market the fiber optic gyroscope, and now stands out as a pioneer and recognized leader on the market. Resulting from over 30 years of research and development, the fiber optic gyroscope is now considered to be one of the best gyroscopes in the world. Its performance is genuinely deemed unlimited.
Our project motivation begins with the GNSS definition. GNSS is Global Navigation Satellite Systems, which is used for extremely accurate and cost-effective solutions for GPS in vehicles and all over the world. There are various forms which each have their own accuracy level and expense for the application. There's the PPP, which is the least accurate, but is also significantly more accurate than normal phone GPS systems used to be. There's PPP RTK, which integrates various amounts of ephemeres, which are corrections from satellites based on the ionosphere and the atmosphere of Earth. And then there's RTK, which is the most accurate system, and it uses base stations placed around the world that create a more accurate signal. In the next slide here, we show a basic diagram of how these are transmitted. So a GNSS receiver with the PPP support is put in the car on the right, which has communications with the satellite and other satellite constellations so that they can communicate and create a more accurate picture. So it's not just a single signal coming down, but it's also reading from multiple reference stations, which would be your base stations, network control stations, and that uplink satellite on the bottom, which gives it the accurate reading based on what the atmosphere looks like at that time. Next, we show our types of GNSS corrections. There is we have the PPP, which is our precise point positioning. The main reason of its lack of accuracy is its latency. This signal takes a long time to go straight to the satellite and come back, and without the use of base stations and other satellite constellations, it's only trying to read off one single satellite. Next, the RTK and PPP, which is more accurate, but it still uses the delay of it having to reach that satellite, which slows down the signal dramatically. The RTK reads directly off of the base stations, and it's the most accurate form. This requires these base stations, as they have to give it corrections and observe based on changing between each one. And then next after that would be the PPP-AR, which is what we are attempting to configure. And this is a PPP system with ambiguity resolution, which aims to decrease the amount of time and latency, without the need for these expensive base stations, using a larger amount of satellites and other broadcasts that come over radio stations.
The anticipated best outcome for the project was a fully operational GNSS receiver capable of performing precise point positioning corrections to the positional data. We also included hardware documentation detailing the components we selected in this project and the justifications behind choosing those components. Software package included a bespoke Linux operating system fully embedded into the design, and with a document detailing the setup and operation of the software, and end result integration, including a final test strategy, final report, final data collected, project progress, and suggested next steps.
Next, we will be discussing if our anticipated best outcome was achieved. And I think the best answer to this is that it wasn't entirely, but there was a lot of good progress made, and we created a product that our sponsors are extremely proud of and that we are also proud of. So what we designed was a functional single-board computer using the IMX6 with an integrated operating system that makes it easily adaptable to new software that they wanted to put on the board. We also designed a fully deployable enclosure that has removable walls to make it easier for them to interface and prototype with it. So basically you can slide these walls up, access every port, or adjust how the board is actually configured inside of this enclosure. The next piece beyond that is our network connectivity and GSM compatibility. So we set it up originally that has Ethernet access and a GSM card on it. And both of these are integrated and they will be easily adaptable for over-the-air updates. And they give access to the PPP corrections through a BNC client. The next is a fully embedded Linux system. That was the operating system that I talked about before. This is extremely capable of adding new software and new systems to it, and it makes it easy and reproducible for our sponsors. Using the documents shown in this last note here, we have a various amount of user manuals and documentation to make it super understandable and reproducible. So what was missing from this? We never got to the point of having the GNSS functionality. We couldn't add the software to it without having issues because of how long it took us to debug the operating system to the point it is at now. The PPP software was also never implemented because the priority of the project shifted, and we focused mainly on the BNC client, which the BNC client is receiving all of the ephemeris from the satellite.
The GSM module we chose for the project was a mini PCLE GSM module produced by Qtcell, the EC25 chip. We selected this chip because it met all the functional requirements needed to provide positional data to the IMX6 board, but also is very easy to integrate because it's a mini PCLE, which the IMX6 has a mini PCLE port. So when designing the operating system, all we needed was a driver to support the connection to the GSM module, making integration very easy. The 3D enclosure that we printed was designed using SolidWorks. The original draft was a enclosure without a top cover or a front wall. This just made for easier troubleshooting and integrating new components into the project. But as the project came to a close, we printed the top cover and the front wall, as can be seen in the picture, and it is a fully isolated unit.
Another key accomplishment to the anticipated best outcome was the integration of the SD card. The SD card served as the onboard storage for the IMX6 board. An SD card is best to use here because it allows for expandable storage and easy replication. However, in order for the SD card to be understood by the IMX6 board, it requires a specific partition table for proper operation. Using gparted, we created an MS-DOS partition table. Leaving 8 megabytes free at the beginning for the bootstrap, we then had to create a 16 megabyte partition labeled boot in a FAT16 file system, activating the LBA flag. The rest of the SD card is partitioned in the ext4 file system labeled root file system. Once this is set up, the corresponding files, images, or libraries can be added to the labels of the boot or the root file system. This method was way easier to use than a terminal fdisk.
The next item on our list is discussing the operating system and bootloader created by BuildRoot. This operating system was created to have a specific user interface that makes it easy for our sponsors to create a GNSS system and understand its functionality with high reproducibility. So this was focused specifically on the board itself. All of the integrated systems and libraries had to be adapted for our board, which is the IMX6. The bootloader is created through a system called Barebox, and this creates one specific also to that CPU and the onboard capabilities. This allowed us to have serial port access and negate the need for an actual monitor and user interface setup. Once this system was compiled, we have the full wiring diagram on this next slide, where it shows how it's set up in the three-dimensional space in the enclosure, but also in the form of a schematic that shows which port is connected to where and how it's connected, because it uses micro USB connections to set everything up. We understand that there's a lot of a higher latency because of these USB connections, but it was not a super high priority to have everything at that super fast speed. So in the future, it will probably be adapted to either USB-C or serial connections to make that latency as small as possible.
Another key accomplishment to the anticipated best outcome was the network interface setup. Allowing the IMX6 to connect to the internet was crucial for our project. Unlike other computers, you must first install the corresponding libraries that contain the commands for the setup. This allows the board to connect to the internet and be able to ping different websites for testing. Pinging is basically sending packets back and forth to the server from your computer to the server and then back to your computer. This also enables the use of the wget command, which is used to easily install libraries and packages needed from websites straight onto the board without having to reload the SD card with the needed libraries.
The next major accomplishment that we made towards this anticipated best outcome was our electrostatic discharge management. So in any project that includes microelectronics or small embedded systems that are very exposed, it is extremely important to keep an eye on the electrostatic problems, because of if you can arc onto it, it could fry the entire board. So our risk assessment shows that the entire board was exposed during the entire debugging process and prototyping. So what we did was we mounted it on a stable platform that allowed it to be insulated away from any grounding on the board. The only points of ground when it turns on is through the power connector, because everything is completely isolated away from a solid metal ground or even just a working platform that has any metal surface. And the other strategies that we use is we mounted it on that board with the countersunk standoffs to make sure that those screws were not even touching the base, but also to isolate it from the other peripherals on the board.
Next, we'll talk about the economic impact for iXblue. One of the main goals of iXblue is to stay up to date with cutting-edge technologies and innovations. As PPIR is anticipated to be one of the major next steps in localization technology, it is important for the company to be able to have its own expertise on the subject. This project will allow iXblue to better understand the stakes of PPIR and thus help to keep updating the products that iXblue offer.
Moving into the individual contribution portion of this presentation, I, Christopher Machalitis, assisted in the creation of the bill of materials, populated Taiga with tasks and subtasks, helped with BuildRoot creation of the operating system, assisted in the design of the 3D enclosure, partitioned the SD card for use with the IMX6 board, loaded the necessary libraries to the SD card for the board to boot, assisted with the proper boot of the operating system, assisted with the installation of the GSM module, and added commands for better use and testing of the GSM module. To further explain these individual technical contributions, the creation of the bill of materials for Phase 1 consisted of using the IMX6 single board computer to understand and utilize the intermediate frequencies given by the radio link's GNSS module, and also use the GSM chip to complete the real-time kinematic GNSS evaluations. The materials needed gave justifications for each part selected. Using Taiga to keep track of our project progression, this tool helped find risks, among other things, that needed immediate attention. The creation of the build root operating system and 3D enclosure was a high priority for our team. This was vital for the project because it includes libraries that are needed for later use as the project progressed. The 3D enclosure offers protection for the components inside and makes for easy access for the board for troubleshooting. Next, the partitioning and loading of the SD card was a very high priority. The SD card was used as the onboard storage for the IMX6 board. In order to be understood by the board, the images and libraries created must be formatted and mounted on different parts of the SD card. This allows for information to be decoded and understood by the board. To further explain the proper boot of the operating system, I suggested doing a clean slate build. This wiped all the files that were messing up the other builds, and ultimately resulted in a fully operational operating system. Once this build was complete, I assisted with the installation of the GSM to the IMX6 board. This process was easy as it just needed to be plugged into the board and tested that it was able to be recognized by the board. Once everything had been installed, more commands were needed to do processes like ping, so data could be received from a source online as intended for this project. Now, I will turn it over to my colleague, Joshua Clift, the electrical engineer, to talk about his individual technical contributions.
Some of my individual contributions to this project include compiling a bill of materials, mounting the IMX6 on a stable working platform that is safe for the electrostatic discharge, populating Taiga with our completed tasks and risks to show that we were always on time and within our time frame of completion, wiring the circuit between the IMX6 and its peripheral equipment, drafting schematics for this circuit and ease of replication by the iXblue team, creating a build root operating system and the barebox bootloader with included libraries so that it made it easy to have the operating system accessible, and updating this operating system periodically and adding network capabilities. So explaining these a little bit, the bill of material was certainly not the most difficult part of the process, as it just created an understanding for all of the team members to know what was going into it and what parts would be used. And we use this to understand where we got the radio links GNSS module, the GSM chip, all the connecting hardware, and anything to make this a better way to design it. Mounting the IMX6 was the next piece, where we used a 1/4-inch thick piece of Lexan, which is ESD and chemical safe, to make sure that it was insulated and away from all of the peripherals. Next was populating Taiga so that we were able to keep on track with our time frame and understand where our risks were so we could keep them in mind as we were working. Wiring the circuit is pretty self-explanatory. It was just hardware capabilities and making sure which ones match up properly, which ports go where, and keeping all the wire management organized. Drafting the schematic was done in AutoCAD so that my hand-drawn drafts were much more clear and understandable and professional. The build root operating system was our most vital part, as it created all of the functionality of the entire board. This operating system allows this computer to have anything and be able to develop further. And then finally updating this operating system with network capability, because this allowed further development using online libraries that were integrated quicker than having to bring them over from a specific computer. And next up, we have Colin Sullivan.
The individual contributions that I made to this project include populating and maintaining the Taiga page, updating the bill of materials, researching and assisting in the selection of the GSM module, assisting in the operating system development, the 3D enclosure drafting and printing, and assisting in receiving and validating data from the GSM chip, and progress made on implementing the BKG in-trip client, otherwise known as BNC. Also contributing to the completion of a user manual for ease of reproduction by iXblue. So just looking at some of my individual contributions in a little more depth, populating and maintaining the Project Taiga page was done on the Taiga website, ensuring that tasks were tracked and design progress was monitored. Updating the bill of materials was fairly important. This was going to ensure that iXblue is able to reproduce the project in their own facilities and continue the work with all the proper components that we selected for the project. Researching the GSM module and ultimately selecting the module was fairly important because it would provide the positional data, or some of the positional data, to the IMX6 board to complete the GNSS calculations. The GSM module was ultimately the deciding factor, was ease of integration, as I discussed in the main points of the project. The mini PCLE chip was fairly easy to integrate into the IMX6 board. The assisting in the operating systems development was one of the hardest tasks that our group faced. Researching the embedded Linux systems and built-root software, really just to provide aid in the development of the software. And then assisting in drafting the 3D enclosure print was a challenge. We used SolidWorks, and we had to do some research to figure out how to get that to run smoothly. But ultimately, we were able to print a 3D enclosure that fit the receiver. So receiving data from the GSM chip was to ensure that the proper drivers were connected to the operating system, so that communication between the GSM module and the IMX6 was enabled. And ultimately, this was a success. The drivers were in place and the GSM was connected. However, collecting data from the GSM chip was not achieved. As well as implementing the BKG in-trip client, the BNC. We did not complete this as a group due to a time constraint, but we did complete pretty thorough research on how to install the software package onto the operating system and provided that information to the iXblue company. So that was a fairly important step. The completed user's manual for the software build was designed so that any engineer at iXblue could replicate the receiver without any prior knowledge. So it had to be formatted very neatly and include a lot of details to ensure that somebody who was not a part of the project could easily replicate the project. And finally, updating the 3D enclosure, adding the sidewall and the top cover, and ensuring the cables can route into and out of the enclosure was an important step in completing the enclosure portion of the project. And up next, Peter Puello will discuss his individual technical contributions.
I'm Peter Palayo, and for this project, my individual contributions consisted of: to help with the completion of the bill of materials, worked with mechanical engineer to complete the 3D enclosure, populate the Taiga page with completed tasks, worked with the group to complete the OS build using build-root and a bare box bootloader, partition the SD card to make it bootable from the IMX6 board using the OS we created, worked with the group to finalize the OS, put necessary libraries and commands on the operating system, and worked with the group to connect the GSM card and receive information. When compiling the bill of materials, we created a list of materials needed for the completion of our project, along with the explanation why each item is necessary and more effective than competing products. When building the 3D model, I worked with a mechanical engineer who has experience in 3D modeling using SolidWorks. We were able to create a protective case for the IMX6 board and all parts necessary. Taiga was a very valuable tool in our project as it allows us to make smaller weekly goals and keep track of all the work completed. When creating the OS using build-root and a bootloader using barebox, this was necessary to be able to run the Linux on the IMX6 board through an SD card. The iMX6 board is only bootable from an SD card. And for this process, we had to use gparted within a Linux system to partition it as necessary. As a group, we were able to complete the final OS. This included all the libraries needed and the commands. iXblue provided the necessary libraries to be included in the OS, and they had to be installed. The commands were necessary to include in our OS for functionality to control the iMX6 board through the terminal. As a group, we worked to connect the GSM card and receive information and display it as necessary.
Wrapping everything up comes with our summary. So our total project ended out as a great success. With physical aspects of our 3D modeling was completed to give iXblue a working solution that they could easily print at another 3D printer that they have anywhere in the world. And this allowed us to create an enclosure that kept not only ours in a safe working environment, but also any other SBCs that they had at their plant. The next piece was our software. We created this Linux-based operating system that allowed further adaptability for any other software that wanted to be integrated by iXblue. Adding on to this, it was being able to have the Ntrip client added to it. It was easy to update libraries, as it was just a quick snap of making the build and then creating an SD card and putting it directly into the iMX6. And then finally was the hardware solution, where the physical hardware was easy for them to follow with the schematics documenting every piece.
Wrapping this presentation up with some key acknowledgments, our Capstone team would like to take the time to thank our technical directors, especially Greg Morvant, for always being around for a meeting or responding via email, and our URI technical directors for all the help they've been providing while still being busy with other work. It was greatly appreciated by our group, and it was a tremendous help while working to achieve the best possible outcome for this project. Thank you.